my name's Derek Lindemeyer. I am the Director of Customer Programs at Overwatch Imaging. We are currently in Oxnard, California, with a team of software and hardware engineers testing our implementation of our Oceanwatch AI software, integrating it with a full motion video gimbal. Our Oceanwatch AI software is designed to automatically identify things that are in the water that are not water. What's exciting about our work with the full motion video gimbal is that we are basically taking an imaging payload that was designed for high zoom and intelligence type missions, and we are implementing a solution that allows us to mechanically control that payload so that it can capture the imagery in a way that we can feed it into our AI models in order for it to basically function like a normal Overwatch Imaging payload operates. What's been great about the work that we've been able to do with the MX-10 is that from the time that we received it until now, which is approximately 3 months total time, we've been able to implement a solution that commands the MX-10 to move in a way that will support our AI models at a speed that we require. The gimbal needed to move much faster than what it normally does. So we've been able to implement that step-stair solution at a frequency that supports providing the imagery that we need for our AI software in just a matter of a few months. And today it's out there identifying surfers in the water and ships at various ranges. And like I said, just functioning exactly like one of our payloads does.
I'm Pierce Martin. I'm a software engineer here at Overwatch Imaging. So my role is mainly focused on kind of capturing images from all our various payloads and time stamping them, getting good geolocation, placing images on the map so that our AI algorithms or further downstream algorithms can process them and create data and useful products for a user. Basically, L3 Westcam kind of just shipped us a big old box with an MX in it, a huge mess of cables and some documentation, and that was kind of where we started. Now we're fully hooked up. We're steering the gimbal around with our own software, performing our own step-stair algorithms. We're capturing imagery from the payload. We're putting that imagery on the map, geolocating it, and we're running our AI algorithms on it and detecting objects in the water, and all autonomously. There's no operator steering the gimbal around or anything like that. It's all done via software. The bigger challenges are first, just kind of talking all the various commands and responses that an MX turret needs to speak in order to drive it around and zoom the cameras and get exposure control, that kind of thing. So that's been one big piece. And then also capturing the imagery from it and geolocating it. That's kind of been another big piece, is how do we tell when a camera was pointed somewhere with the MX, how did that relate to the real world? Where did it actually end up on the ground in terms of a footprint?
Justin Fernandez, I'm a software engineer. So I've been developing our AI pipelines, developing object detectors to find people, boats, not boats in water. The first step in the process was taking data from an MX-10 and pushing it through our software just as a proof of concept to see if we could detect things and find information in their imagery. Then once we found that worked pretty well, we did a more tight integration where we are, instead of reading from a processed data stream, we're reading from a more raw data stream from the payload, and also doing a tighter integration with respect to command and control of the payload. We train our AI, our boat finding networks, on mostly our own imagery, and we've found that as long as we can match the ground sampling distance, the real size of a pixel, that our models transfer very well to other EO or RGB sensors, including the ability to also process visible spectrums, such as infrared. So we've proved that we can steer the system. We've proved that we can read their data, make meaningful detections based on that data. And so this week is really about doing some fine-tuning, making sure that the settings that we're using for scanning and the settings that we're using for detections work well within some certain concept of operation. So we're out there looking for small targets, looking for people in the water, looking for boats. And when you're looking for different types of objects, you want to use the system differently. And so we're configuring parameters to automate that process and make it seamless for users. Understanding the capabilities of the sensor, and so that's knowing what GSD, what ground sample distance we need in order to detect a certain type of object. Understanding that information will allow us to operate the sensor in a manner in which is useful. If we know that we can detect objects, detect people in the water with a certain GSD, with a certain number of pixels, then we're not going to steer the system in a manner where the camera is generating data that will not be compatible with that performance metric.
My name is Kelsey Ramsey. I work at Overwatch Imaging as a software engineer, and my work primarily revolves around the user interface. A lot of the software behind the scenes is responsible for classifying objects in water. We also have a front-end user interface that brings those detections to the operator's computer. The front-end user interface operates through a web browser, so there's no software to install other than a web browser, which hopefully every laptop or computer will have one of those. The user interface is essentially a map with a couple sidebars where you can turn cameras on or off or change a couple settings. And when we detect objects in the water, a pin pops up on the map and it gives you the information that you need to then slew your gimbal or make the phone call to search and rescue. The interface has a few options so that you can command the camera system to search for a specific type of object in the water. You can look for swimmers, you can look for boats. So you have some control over those targets that come into the user interface. The software that we've developed can control any third-party video gimbal to use the correct zoom and field of view so that we can achieve appropriate GSD, so that if we're searching for a small object, we can get the minimum number of pixels on that object, 10 pixels, let's say. If we're searching for a big boat, we can zoom out and we can get the minimum number of pixels on that, which would then allow us to search an even wider area. You got a small installer, you put it on there, and you press automatic search. You choose the object that you're after, and then it starts scanning. We've got chips that we display to the user. We've got high resolution chips, which we call super chips, and then regular chips, which are really lightweight and easy to transfer in between the payload and the operator workstation. If you send high resolution images of every chip directly to the user interface, that can slow things down because the imagers are such high resolution. It's difficult to display that much information as quickly as we capture it. So that's what our sort of machine learning algorithms are for, is looking through those images and determining which ones the operator should take a second look at.
So we just closed out our last day here at Oceanwatch Week. Our time down here has been absolutely phenomenal. We've made huge strides in our Oceanwatch AI software. We've also made huge strides in our implementation with the full motion video gimbal that we're working with right now. And we think that this really sets us up with a great launch pad to continue working on this really awesome solution set that we have here at Overwatch Imaging.